So hello everyone, my name is Mati Čorak and I'm coming from University of Zagreb. And today, topic of my today presentation is polynomial smoothing using Chebyshev polynomials. So this is the overview of today's presentation. It is divided into 4 sections. And to start with the introduction. So this research is funded by the Hexaphone project, and our research group is a part of the work package 4, which is focused on highly parallel solvers and linear algebra solvers. This slide I think I can skip. And here we can see the typical CFD workflow, which is divided into 5 sections, and we are focusing on the 4th part, which is solving simulation. So for a solver, we have chosen algebraic multigrid, which is a powerful numerical technique which is used for in solving large system of linear equations, and it has some typical workflow is consists of 3 steps. First, AMG constructs a hierarchy of grids from fine to the coarse one. Second, we need to coarsen the problem by reducing the number of unknown at each level of grid hierarchy. And the third part is the smoothing, which is technique applied to reduce high-frequency errors. So, as I said, algebraic multigrid has proven to be efficient scalable solver, but HPCs present new challenges for their scalability due to intensive CPU communications. And on this picture here, we can see what is smoothing and what is coarsening. If we look at the first picture here, we can see the difference between first and the second. If we apply smoothing procedure, we can see that we get rid of the high frequency errors. And difference between third and the second, we can see if we apply coarsening algorithm, we can see that we are getting rid of the low frequency errors. So this procedure, as I said, coarsening, it's typically done with a V-cycle, which is iterative approach in multi-grid method. As I said, it is navigating through the grids by descending from the finest to the coarsest level. And it is the crucial role in accelerating the convergence of the linear system. As we can see from the picture below, after coarsening, we are applying smoothing on the each level, and we are going from the coarsest to the finest mesh back again. We are again applying smoothing. So, smoothing procedure. As I said, the goal of the smoothing procedure is reducing the high frequency components of the error in the approximate solution of linear system. Some of the typical smoothing algorithms used are Jacobi method, Gauss-Seidel method, successive over relaxation, ILU method, and polynomial smoothing. So, and the goal of this method is to dampen oscillatory error components and making the residual smooth and more suitable for the coarse grid corrections. Here we can see some advantages over other iterative methods. So polynomial smoothing advantages over other iterative methods. First is efficiency, so it can achieve nil optimal convergence results in prescribed eigenvalue ranges. Second is robustness, so it works over a wide range of eigenvalues by scaling and shifting the polynomial. Flexibility, we can control the degree of polynomial, so we can adjust the strength of smoothing operation. And in parallel performance, it involves only matrix vector multiplication, which is easily parallelized, and it reduced synchronization overhead. So if we compare polynomial smoothing to the other smoothing methods, for example with Jacobi and Gauss-Seidel, they are simpler and more easy to implement, but they require more iteration to achieve sufficient smoothing, and they are less effective if the eigenspectrum is wide. Next one is successive over relaxation. It is better than Gauss-Seidel, but has some of synchronization issues in parallel implementation, and it is not handling well wide eigenspectre as polynomial smoothing. ILU, it is way better than Jacobi and Gauss-Seidel, but it is computationally expensive. We need a lot of memory to store all the solutions, and it is way harder to parallelize than polynomial smoothing. Of course, polynomial smoothing has some of disadvantages. For example, it is complex to implement. It requires spectral analysis of system matrix. It can have oversmoothing issues, which means that we can achieve, let's say, too strong smoothing, so we can even get rid of the low frequency errors. And parameter tuning can be difficult sometimes because it is really case dependent. So to use polynomial smoothing, we are using Chebyshev polynomials, which are sequence of orthogonal polynomials that arise in the context of approximation theory. So we need to minimize the error at the AB interval, which is typically from -1 to 1, when, so we can see where the eigenvalues are. Workflow of Chebyshev polynomials that we need, first we transform our data or the matrix, as I said, to the interval from -1 to 1. Then we estimate eigenvalues. Then we compute Chebyshev polynomials, construct smoothed polynomials, and then do this evaluation with polynomial. So here I can show you what I have done until now. Okay. So the most difficult part here, at least for me, was estimating matrix spectrum. As first idea was to use Grigorian circle theorem. So main idea here is that radius of the circle would be sum of the all non-diagonal element in our matrix, and the circle center would be diagonal element. And the crossing between, I will show you next what the solution looks like. And we expect that eigenvalues are found inside the circle. Of course, some disadvantages that can overestimate, and it sometimes cannot give sharp boundaries. So to see what is it good or not, we have done testing for Poisson pressure equation for incompressible Navier-Stokes, which yields positive definite matrix, and it is done on cavity and backward-facing step. So first test case is cavity. On the left we can see discretized domain, and on the right we can see these circles. So as I said before, center of the circle is diagonal element, and these circles which are overlapping now are the radius. So sum of the all non-diagonal elements. Blue dot here represents smallest eigenvalue, which is calculating in different way than with this Grigorian circle theorem, and the red one is the actual maximum eigenvalue. And here we can see that the difference between calculating with this theorem and the actual value is less than 1%, which is really good result. Second test case is done again for the cavity test case, but it is now done for non-uniform mesh. And now we can see more circles because they are not overlapping each other anymore. But here we can see that this red dot shifted towards center, which means that we get about 4% difference for the largest, and the smallest one is still 0, which is still something that we can go on with. So the next test was done for backward-facing step, and now we can see this is for uniform mesh, and we can see that difference between largest eigenvalue and the actual one is 13%, which can be a bit of the difference, difficulties for later stages. And while I was doing this, I didn't know that we need to multiply largest eigenvalue by some factor, which is 3 to 5% according to this article here. So at this stage, I was like, I need to find another way of finding matrix spectrum. This wouldn't work, and just to be sure if it's good or not, I have done one more test case, which can see it is different about 15%, which is not acceptable anymore. So, this means that we need to find another way of finding matrix spectrum, which is using power method, which is iterative algorithm used to find dominant eigenvalue and corresponding eigenvectors of the matrix. So drawbacks, it find only single largest eigenvalue, and it can sometimes be slow in convergence. But if these drawbacks or not, we will see in our test cases. So to see performance, I have done again test case for non-uniform mesh for cavity, and on the left side we can see actual eigenvalues and number of iterations which are needed to achieve them. And on the right side we can see a residual and number of iterations, and we can see that in this is like 13 iterations we achieve satisfying results. If we take into account that we need to multiply this by 3 to 5%, I think this is quite nice results. And the second test case is for backward facing step for non-uniform mesh, and we can see that we achieve the same result even in less iterations. So fortunately that's it what I have done today, because I didn't, this took me way longer than I thought. And this is initial phase of making a new smoothing algorithm, which aim to test the solver to the limit of scaling capabilities. And our plan is to scale this problem on HPC and test it on the larger cases, which are hundreds of millions of cells or larger. And we expect to achieve excellent results due to efficient utilization of computational resources rather than extensive data transfer between processors boundary. And as a conclusion, we have seen that the Grigorian circle theorem does not really work in the real life application, and we need to use more complex power iteration to get accurate results. And we saw that power iteration is a great tool and give us great results, but it's a bit more complex because it is evolving matrix vector multiplication, which can be potential challenge for for big matrices. And as a future work, as I said before, we need to scale this to parallel problems and to test it on large test cases to see if it's working or not. So thank you all for attention, and please, if you have any question or suggestion for me, what can I do? I can do later, please. Talk to me.
Is there any question?
Yes.
So I've seen previous work under the Hexaphone project.
Okay.
I guess this is another part of that work, or is it?
It is connected, but there's something, as I told, it took me way longer than I thought it would be, so it isn't implemented in the Hexaphone, but they are financing my PhD, so I have to put it there.
And so my question was, well, two questions. First, this approach, we're going to this approach to actually lower the communication cost, so that the multigrid method could scale better. Is that
yes. So smoothing procedure and multigrid method. For example, for now, I think the most efficient is ILU, but ILU smoother. But if you take the ILU in parallel, it has a lot of communication between near diagonal. It stores all the elements, and you need to push it through the processor boundary every iteration. And with this, we want to go around this and not to have that communication every time. So we think it will be better and faster.
So this approach of polynomial, is it implemented in other previous works on this subject, not in OpenFOAM?
As I see, not. And even looking at other libraries and all, I didn't saw it yet. So it's all now. It took me a long time because this is mathematical theory which need to be put in OpenFOAM, so it's a bit difficult for me. So.
So it's a new idea.
Yes. So it should be tested definitely.
Okay. Is there any question? I have small questions. First, why do you choose the Chebyshev?
Because I find it would be probably efficient, but if you have any other suggestion, please tell me what I can use. So.
Okay. The other one, because my research I focus on the high-speed flow. So I'm curious about if your method can be applied in other high-speed servers.
I can really answer you that straightforward because I'm not sure. So maybe I should investigate a bit more and.
Okay, fine. Okay. We are coming to end this session. Thank you all. Thank you.